of discussions with members from the STAN team and other people who are quite informed about Bayesian modeling. So what I'm talking about today is a problem, especially when you start, not only when you start with Bayesian modeling, but especially when you work a little bit longer with Bayesian models. It's how to choose informative trials. If you've heard about Bayesian modeling before, you probably heard about priors, choosing priors and combining prior and likelihood to get your posterior, which is effectively the result of a Bayesian model. This is what I'm talking about today, because this is something which is not so intuitive, and there are not many practical examples. So I hope this is something which will be helpful for others who want to start with this topic. So short overview of my agenda. First, I will introduce you to an empirical example. So this is a real-world example here, what I'm talking today about, and how to analyze this data with a simple regression model, and what are the difficulties when using simple regression, and what are the advantages of using Bayesian models. And then, after giving a short introduction to the principles of Bayesian modeling, I will switch to rstanarm, a package from the STAN team. Who of you has not heard of STAN before? Okay, STAN is a probabilistic programming language which is designed to fit Bayesian models. It's an own language which has interfaces for different other languages like Python or R, and you have the rstan package, which is the classical interface to STAN for R. And rstanarm is a package which makes it very easy to start with Bayesian modeling in R without completely knowing the syntax in detail for STAN. Other models are, for example, packages are BRMS, Bayesian Regression Modeling with STAN, from Paul Bürkner from Münster, which is also very easy to use because it's based on the classical R formula syntax, and it makes it easy to interface or interfere with STAN. And finally, I will show you examples for regression models and the different forms of priors. Okay, this is a project I'm currently working in, and which is almost finished. And it's about two hospitals here in Hamburg, and it's about special concepts for providing care to people with dementia. There are two hospitals with internal medicine, one with the regular treatment and one with a special treatment which focuses on the difficulties you have when you work with people with dementia. And known problems when you have patients with dementia is that they have a higher fall risk or a higher risk for delirium, etc. So there are many difficulties in the treatment because people with dementia don't behave like normal patients, and that makes it difficult to care for them and causes several problems probably. So I wanted to know factors that explain the risk of falling. This is one of the outcomes of interest, and from literature we know that dementia, especially severe dementia, is associated with a 3 to 3.7 fold higher risk of falling. So dementia is a risk factor for falling, and my outcome was fall incident during a hospital stay of about 7 days, and fall yes, no. So binary outcome, so logistic regression model, and predictors are age, gender, mobility, severity of dementia, and some others. And what I want to focus now especially on this predictor in the following examples, on the association of severe dementia and fall risk. So whenever you see odds ratios here, it's only the odds ratio for the category high or severe dementia I'm talking about, and how the risk increases according to fall incidence. Okay, so we have the special care unit for patients with dementia, and we have 526 cases and about 10% fall incidence in our data. So 52 patients did fall during the hospital stay. And from those 52 patients, there were 1 with mild dementia, 14 with medium dementia, and 73 with severe dementia symptoms. And now I have this formula, just give fall, yes, no, and the covariates, age, dementia, etc. And I fitted a simple logistic regression model, GLM, model formula, data, and a nominal link. And this is the result, the odds ratio for severe dementia. And you see, this is a rather conspicuous value, an odds ratio of about 8.6, when it's known from literature that we have a risk or odds ratio of about 3 to 3.7, and the confidence intervals are very large. So this is reaches a parameter space which is absolutely nonsense, actually. So what to do? Bayesian regression modeling is a solution for this problem, but not only, you can also use other models, Bayesian modeling is, in this case, helpful because you can also include the prior knowledge, the risk of 3 to 3.7 higher fall risk with severe dementia. And so I decided to start with Bayesian models. So what does Bayesian modeling actually do? The advantage is Bayesian models can better cope with small sample sizes. This is due to the Bayes theorem. You have a likelihood, this is your data, and your prior knowledge, and this will be combined to get a result. And if you have small sample sizes, this approach helps you to keep the results in a plausible parameter space, on one hand. And another thing is that the sampling technique, Markov chain Monte Carlo sampling, allows you to fit even models with small data size or small sample size because the bias is reduced due to the sampling technique. And another, in my opinion, very important advantage is you have no p-values. Many people want to have p-values and like to have p-values, but if you're a little bit more into this topic, you know that a p-value does not, or is not related to the evidence of an effect. So having no p-values can be quite relaxing. Okay. Actually, you can use other models as well with penalized likelihood, like the logist F package, which does also shrink parameters, but this is not very practical here to demonstrate priors, so I just focus on Bayesian modeling. And I start from the back, from behind. So when you have fitted a model, what you get as a result is the posterior distribution, and this is the distribution of multiple plausible estimates. So you do not get just one point estimate when you compute a Bayesian model, but you get, by default, 4,000 different estimates distributed in this way, which is called the posterior distribution. So you have estimates which are more plausible, and you have estimates which are less plausible, but actually you have a space or a distribution of estimates of associations between your independent variables, which are all possible. And second is you don't have a confidence interval in the classical frequentist sense, but you have so-called uncertainty intervals, which describe how likely a value is within which range. So we can compute a 90% uncertainty interval, and it says with a 90% probability, the true effect lies between the upper and lower limit. This is something which typically is done with the frequentist intervals, but which is actually not possible to conclude. But it is possible to conclude this with Bayesian modeling. Okay. So if you want to fit a Bayesian model, how to do this? It's actually quite easy. You simply load the package rstanarm and take your your classical model and just prefix it with scan underscore, and that's it. So I have exactly the same model as before, just print stand underscore or put stand underscore before, and then you have calculated your Bayesian model. And it is quite convenient, this package, because it offers the classical methods you know from other models as well. You can use the runif command for mixed models like an LME4, etc. So it's the same behavior as the classical models, just as you have fitted a Bayesian model. And the difference is you don't have just one estimate, I said that before, but you have 4,000 samples of estimates for each variable. So you have the sDataFrame method, and this returns a data frame with 6 variables, each of your independent variables in the model, and 4,000 samples, 4,000 different estimates. Okay, now when I've done this, you can compute not a point estimate like in a classical model, but a posterior median. This is the posterior median is a little bit comparable to the point estimate. And if you do this, you have an odds ratio of 6.57, and this is the confidence interval, and you have no p-value. So just using the Bayesian model gives you a little bit more plausible value than the classical logistic regression. But it's still a little bit conspicuous. So, but it's a little bit better. That was a feedback from the STAN team members. I have to point out that there is actually no point estimate in a classical sense, but the posterior median is the expected absolute, the value that minimizes the expected absolute error, just for technical protocol. Okay, now you fitted a model, a Bayesian model here. But you can't see any prior information. So I said Bayesian modeling is all about priors, including priors, but here is no prior defined. So how do are priors included in the model? This is the result, the posterior, and this dashed line, the likelihood, this is the result from the simple regression part of your Bayesian model. And the prior is the information you put into the model before it sees the data. So what Bayesian models do is they penalize the data if you have small sample sizes. So if you have very large samples, the impact of the likelihood of your data is stronger than the prior knowledge. And in the other way around, if you have very few samples, if you have just a few cases, then the impact of the prior knowledge is stronger. And this is what regularizes the parameter space to a plausible value space, and which prevents parameters or estimates from getting out of bounds. Okay, so how to choose priors? The worst prior is a flat prior, because this is a uniform prior. It's just a flat line, which makes all values equally like or equally probable. So this is what a classical regression does. So you should actually never use a flat prior in your model. What works quite well are weakly informative priors. Weakly informative priors are the defaults in rstanarm and other packages as well. And these priors work for almost any or all situations. They work quite well. And this is why the default modeling in rstan is so easy, because it automatically applies weakly informative priors, so you can run Bayesian modeling without knowing or having any prior knowledge, special or concrete prior knowledge. Okay, what does this mean? You have your estimates, and the prior assumes a zero effect, no effect, and is a distribution. So your estimate is around zero and within a certain space, a location and a standard on a scale around this location. This is what STAN or Bayesian models consider as default range, plausible range for your estimates. And you have to remember that this is on a logit scale, so this value exponentiated is around 140, so this is a possible odds ratio of about 140, so it's not very narrow, but it's still conservative enough to prevent estimates being out of bounds. And rstanarm adjusts this price internally, so if you have default weekly informative priors, rstanarm checks the variables, and for variables with a large range, like age for example, this scale parameter is adjusted. If you have age from 10 to 100, the coefficient is usually relatively small, and according to this, the scale is also very small, so the adjustment works quite well and it is conservative. So what does a weekly informative prior do? To summarize, a weekly informative prior rules out very large effects, so that's why it's called weekly informative, and the centering around zero means that the model assumes both negative and positive associations are equal likely, and this is why the estimates are regularized. So it's very conservative and typically more conservative than classical models. So if you have weekly informative prior, then this is our prior knowledge from our model we've just fitted, and this is the result, the posterior, which is computed by our possible parameter for dementia, severe dementia, and what we have found from the data, so this distribution of the data, and the result is this possible parameter space. And what you have here is a median of 1.88, and now this is all on the logit scale, on the linear scale, and if you exponentiate 1.88, you get the odds ratio of 6.57. This is how you translate the posterior median into the odds ratio. Okay. Probably it's a little bit difficult to follow. I hope it will become more clear when I show the next example. Weekly informative prior. The next thing is we can use informative priors, and this is a little bit more difficult because with weekly informative priors, just run your model and have the results. Informative priors means you have a certain knowledge about the distribution of your parameters. Here you assume you have no knowledge, so you assume a neutral distribution. But in this case, we know that high dementia is associated with a odds ratio of about 3.5 with fall risk, and medium dementia with an odds ratio about 2. So we have to transform this on the linear scale. We take the log of these odds ratios and we put this into the prior information of the model. So what we are doing here now is adding a parameter prior to our model definition, to our model formula, and we leave the other variables where we have no prior knowledge, where we have no information, we leave them at default values, and we have our knowledge included into this location parameters. And we don't have any concrete information about the scale, about the distribution, about the range, so we leave this at default for the first. Okay. And this is what we get now. And you see, this is the prior distribution of our second model. And you see it's located around 2. This is, something about 2.13. And this is the prior knowledge we have now for our new model. And this is the posterior for our second model, which is a little bit more narrow, and this is the posterior median, so we have an odds ratio about 8.47 in this case. And it's not surprising that this odds ratio is larger again, because in this case we had prior information which assumed no effect, so a location around 0 for our log odds, and in this model here we had assumed a location of our prior around 2 and 3.5. 3.5. So it's not surprisingly that the prior information is shifting to the right into a positive space, and thus our results are positive as well, or larger or higher as well. So to compare, the light blue here is the posterior or results from the first model, the dark blue of our second model, and you here see this is the prior information, the weakly informative of our first model, and this is the informative prior of our second model. Okay, now we have also knowledge about the outcome. Fall incidence typically is around 40%, varying from 30 to 60% in hospitals. So people with dementia have a fall rate of 30 to 60% in hospitals, and we can include this information in the model as well. This is the outcome which affects the intercept, so we have a prior intercept. And to translate the probability into a linear scale, we need the q-logis command, and so p-fall is q-logis 0.4, which is 40%, and we have a scale about 0.5, because if you compute q-logis, etc., you have a range of about 28 to 52%, which comes close to this, exactly close. So we have now information on the fall incidence of outcome and the range, the scale. And we now have an odds ratio of about 5.7, which comes closer to what we know from literature. This is our posterior median. And if we now compare the three posterior samples, so to make it, to get a better view and not to confuse, I have just plotted the posterior samples. The red one was our weakly informative prior, our first model, neutral information, so to say, and this is our second model with the informative prior for the illustration, for dementia, and this is our third model with the informative information about our outcome additionally included. Okay, and now we know from literature that not only the association between dementia and fall incidence, but also the confidence intervals. We know odds ratio is about 3.5, and confidence interval was from 2 to 7, and if we translate this into linear scale, it's about log point 2.5, and we can include this into the scale parameter from our prior argument as well. And we need to remember that, this is just a technical detail, that rstanarm adjusts the scale according to the metric of our independent variables. And since we have just a yes-no, severe dementia yes-no, there's no adjustment. For age, for example, we would have to multiply with the standard deviation. That's just a technical footnote. And this is our final model. You can see the prior distribution is a little bit narrower than the others before because we specified a range. We limited the range from 6 to 11.9 for our model with informative priors, including user-defined scales, compared to our simple logistic regression model, which has odds ratio 8.7 and 1 to 161 as confidence interval. So here are the four models, the posterior distributions, our results, the distribution of our estimates plotted, and you see what we have done here. It's very narrow. We have probably regularized too much here in this case because it's very narrow. There is not much, we do not allow very large values here, so it's probably not the best model. But I think it's good for demonstrating how prior works. Okay, so to conclude, Bayesian models have many advantages, especially the technique. The sampling technique, Markov chain Monte Carlo sampling is helpful if data is good or if you have small sample sizes. And the default prior knowledge ensures that parameters estimates are on a plausible space, so you don't have any confusing or implausible values, Weakly informative priors work very well, actually, and in certain cases also outperform the informative priors. But if you have informative priors, you can even reduce the bias being more conservative, but you have to take care of defining the scales and location values of your informative priors, because if you narrow down the effects too much, you probably would really distort or have a bias in your results finally. So I think that's this. There are some tips for visualization or for reporting Bayesian models. You have this is our result. It's a result of 4,000 estimates. So you don't have the exact point estimates. That's why for Bayesian modeling it's typical to report a range of plausible values. What you have here is the 50% and 90% interval. So you can say, when you fit a Bayesian model, you can say with a probability of 50%, the true value, the association between our dementia, severe dementia and fall incidence lies within a ratio of 3 to 6 about. And this is a probability statement you can easily make with Bayesian modeling, but which you cannot make with frequentist models. So if you have this odds ratio, you can't say it's an. You do say it's the odds are about 8-fold higher, but actually you can't say this for sure. With Bayesian modeling, you can directly conclude the probability of an association between estimate and outcome, which is due to the sampling technique, etc. And that's why it doesn't make sense to compute different, at least 2 different intervals to have an idea of the effect you have measured. And yes, these are quite useful packages for visualization, and these people either have helped me with checking that everything is right, what I'm saying here, and correct, and will provide useful information when you start with Bayesian modeling and rstanarm. Okay, thank you.